All right, I'm going to try to record this so students can see exactly what to do. I'm using Polypad, our digital manipulatives website we've used before in class. And let me move over here to number 1. This is for the Algebra 1, Unit 1 study guide. Each skill that you see listed in here in questions 1, 2, 3, 4, 5, 6, and 7, I'll slide that over, 6, 7, 7B. All of these skills will be on the Unit 1 test. So let's go ahead and dive into it, starting with question number 1, which is A, B, C, and D. Approximate each radical to the square root of these numbers to the nearest whole number. And how we're going to do this is students will use the perfect squares, which is any number times itself. So for example, 1 times 1 will be 1, 2 times 2 will be 4, 3 times 3 will be 9, 4 times 4 will be 16, 5 times 5 will be 25, 6 times 6 is 36, 7 times 7 is 42, 8 times 8 is 64. Small mistake right there. 7 times 7, 49. Alright, cool. So then once you have your perfect squares listed out, let's take, for example, the square root of 17. So with the square root of 17, we're going to see which two perfect squares does it fit in between. In this case, that's the square root of 16 and the square root of 25. So the square root of 17 will go right in between those two perfect squares. Now, because these two are perfect squares, you can actually find which numbers these are. And in this case, the square root of 17 is going to go in between 4 and 5 on the number line. So it'll be something like 4 point something something something. The specifics in this case don't matter. We just want to round it or estimate it to the nearest whole number. It's in between 4 and 5. So after that, scholars will go through and do the same thing for B, C, and D. Now C looks a little different because the square root of 8, the radical 8, is the numerator. However, it'll be the same process where we see the square root of 8 goes in between 4 and 9, which will do the square roots of 4 and 9. In this case, it'll go in between 2 and 3. So in this case, 2/5 and 3/5. In between those will be the square root of 8/5. It's somewhere in between 2/5 and 3/5. And that's it for approximating radicals. Moving forward to set operations, looking for the intersections, unions, and differences. Now, the hardest part of this for students was learning the math lingo. However, once they learned the lingo, this was actually pretty easy. The intersection is looking at, in sets A, these numbers, and sets B, these numbers. So set A, we can label our Venn diagram, A and B. The intersection is the numbers that both sets have in common. So they both don't have 1 and 2. However, they both have 3, 4, and 5. So it's where the numbers intersects. Right, so A has 1, 2, 3, 4, and 5. 3, 4, and 5 being intersection. B has 3, 4, and 5, and 6, 7. All right, so those answers for intersection will be 3, 4, and 5 right here. Union is just a combination of all the possibilities of A and all the possibilities of B for information, for data, for these numbers without repeating. So union will be 1, 2, 3, 4, 5, 6, and 7. All of those answers will go here as a union of sets A and B. For the difference of sets, it's what set A has that set B does not have. So in this case, set A has the data 1 and 2. B does not have 1 and 2. It has 3, 4, and 5, but it doesn't have 1 and 2. So 1 and 2. And we're going to close our set with braces. That's the only other thing. It's not the best drawing on this computer, but yeah, braces looks something like that. Similar to the brackets. All of the data, all the elements go inside the braces. So for union, again, that'll be 1. Those are all the options. 3, 4, 5, 6, and 7. Moving on to question 3. This is another question that looks more complex than it really is. The hardest part was learning the math lingo, which we digested. So this just says that x, which is whatever number in the set that we're graphing, the element of that is a real number. So the characteristics of the numbers we're looking for are real numbers. We talked about numerical sets, starting from counting numbers, the natural numbers, to whole numbers including 0, to integers including the negative numbers, and then leveling up our understanding of numbers to real numbers, which includes fractions and decimals. So it can be all of the above, these numbers that we're graphing. But we want a simple way of showing that. So there's 2 ways you can do that. You can either show on the number line, or you can say x is in between certain numbers. We're going to use the number line example because it says graph the sets that satisfies both inequalities. So if I'm drawing my number line, the first property is x is greater than -2. So I draw my number line, start with 0, -1, -2. X is greater than but not equal to -2. So that would be an open circle above the -2. This symbol right here means and. So and x is less than or equal to 3. So I'll draw my positive 1, 2, 3. Because x can be equal to 3, it'll be a closed circle. And all the numbers in between on this number line fulfill the properties of x. Greater than but not equal to -2, less than or equal to 3. So scholars will do the same thing for number 2, right? And again, these are real numbers, so it could technically be x could be -1.5 or 2.2 because real numbers include those decimals and fractions. So here, same thing. X is less than or equal to 0. You use a closed circle on that 0, something like that. And x is greater than -4. So I can extend my number line here to include -3 and -4. And it could be equal to, so another closed circle. So x is less than 0 or equal to 0, and x is greater than or equal to -4. So this would describe number 2. And that's fulfilling the qualification of graphing that on a number line. And all the numbers in between that could be fractions or decimals and the negatives. For number 4, the recursive formula says given recursive formula A1, we learned that subscript 1 means the first term in the sequence, whatever the first number is. For example, if we scroll up to number 2, we see the first term was 1 in set A, and set B, the first term was 3. So that's all the subscript represents. So when the subscript is n, that can mean any term you're talking about plus 1 will be the next term over. For example, we're talking about n being the first term plus 1 will be the second term. And you'll take that term and just add 3 to it. So if the first term is 5, the next term is 3 more to that. So 6, 7, 8, 9, 10, 11, 12, 13, 14 would be the next 3 terms after the first term. That's A1, A2, A3, and A4, the first term. Pretty simple once you get over the lingo. For 4B, given the sequence 8, 16, 32, 64, write the recursive formula. Now, the recursive formula needs 2 things. We look at 4A, you need the first term, and you need it what you were adding to it or subtracting from that first term, or what you were multiplying, dividing from that first term. If you're adding and subtracting, we call that an arithmetic sequence. if you are multiplying and dividing, we call that a geometric sequence. So here we see that the first term is 8. So A1, the first term is equal to 8. And then what operation is happening to go from one term to the next, and then that term to the next? In this case, it'd be times 2. So we can write that as a n plus 1 is equal to whatever term we're talking about, because we could be talking about to go from the third to the fourth, would be times 2. And we usually use the dot for times in algebra, saying as though x is normally taken for number 2. Looking at number 5, A and D, determine whether each sequence is arithmetic, geometric, or neither. So looking for A and B, again, arithmetic was, are we adding to go from one term to the next? Are we multiplying to go from one term to the next? In A, it looks like we're just adding 4. So I can label that as arithmetic. In B, it looks like we're dividing by 3. Division is the opposite of multiplication, so we'll call that geometric. In C, we see adding 2 and then adding 3 and then adding 4. So there's no particular pattern for the operation, so that would be neither. 5D looks like it could be neither. However, you could be multiplying by 1, which would mean that this is actually a geometric. So go from one term to the next. 5 times 1 would be 5. So it will be categorized as a geometric sequence. Looking at number 6. Write the explicit formula and find the given term. So again, the first term is 3. A1 is equal to 3, and that should have been a subscript there. It's arithmetic, so we're adding the difference, which is 2. So again, we put our numbers, our terms in the braces. The first term is 3. The difference is 2. So 3, 4, 5, 6, 7, 8, 9. However, it says find the 12th term, which means we could do this all the way to get to 12, but there's a formula where you can jump straight to the 12th term. That formula is in our students' notes. However, the formula is any number is going to be the first term plus the term number we're looking for minus 1, the subscript, times the difference. So once we have the correct formula for arithmetic sequences, we can just plug in the numbers. So again, the number term that we're looking for, A12, we're looking for the 12th term. It's going to be equal to the value of the first term, which is 3, plus the number of that term, again, we're looking for is 12. How n was 12 here, the value of n is 12 here, minus 1. We can simplify that to 11, times the difference. The difference here is 2, so times 2. After we plug in the correct numbers, we use orders of operations. So we know we're going to do, again, parentheses first. 12 minus 1 is 11. And then we're going to multiply before we add. So 11 times 2 will give us 22. And then we can add the 3. 22 plus 3 is 25. So our 12th term is equal to the value of 25. For geometric, there's a similar formula, but the formula is different. The geometric explicit formula to find exactly the 6th term without having to go in order from 1 to 2 and 2 to 3 and 3 to 4, and to jump straight to the 6th term would be whatever term we're looking for, in this case the 6, is equal to the first term plus, make sure I have the correct formula, sorry, not plus, times, going back, the first term times the ratio, aka where you're multiplying to get from one term to the next. And for the exponent of that ratio, it's whatever number term we're looking for minus 1. Once you know that, you go ahead and plug in the numbers. So again, we're looking for A6. The term we're looking for is 6. The first term is 2. So that's 2 times, I guess that could be a times there to avoid confusion. The ratio is 3. that n, again, n was 6, so 6 minus 1. So our exponent here is 5, 3 to the 5th power. Once students do that, they can go ahead and multiply. So 3 times 3 times 3 times 3 times 3 is 243 times 2, our first term, will give us A6 is equal to 486. Right, that's a whole lot easier. We can plug in the formula and jump straight to the 6th term instead of having to go in order. Next, moving on to 7a, write and solve an equation to find the number. You want to rationalize this equation first and break it apart into pieces to write the expression or write the equation. For example, starting with 3 more than twice a number. Well, we don't know what that number is. It's unknown, so it's x. The twice that number x could be represented as 2x, and 3 more than that will be plus 3. Is usually represents is equal to, same thing as are or were, the same as 5 less than 3 times the number. Again, we can start with the variable, the number. We don't know what it is. 3 times that number will be 3 times n, so 3n. And 5 less than that, you're going to add the negative 5 or minus 5 at the end, because the order actually does matter. Once you write the proper equation, then you can solve it using our SCAM method, which means how to solve equations using simplifying by using distributive property, if there is any, combining like terms, if there is any, doing the inverse operations of addition and subtraction, and then the inverse operations of multiplication and division, with the ultimate goal of isolating the variable. I'm going to make one correction here. I use n right here. I kind of want to keep the variable the same, so that number is just x. The variable doesn't matter as long as it stays the same. So now we need to isolate x to one side of this equal sign using our operations. Everything in math is built off of the 4 arithmetic operations. You're typically either adding, subtracting, multiplying, or dividing something. We build upon that. In this case, it's easier, I'll change colors, to minus the 2x on both sides. Our students know what you do to one side, you always do to the other. That keeps the equation balanced, it keeps it equal. And now we're left with 3 is equal to x minus 5. Our ultimate goal is to get x by itself. So again, we're using inverse operations. I cancel out this negative 5 with the positive 5. And that gives me my final answer, which 5 plus 3 is 8. So 8 is equal to x, or x is equal to 8. Problem 7b is very similar. However, you need a way to express consecutive integers. In this case, consecutive even integers. And the way we're going to express that is whatever the first number is, say n, the next even number in order, because consecutive means numbers in order, like 3, 4, 5, 6, can be represented as n plus 2. All right, so if n is the number 4, right, n is 4, then the next even number will be plus 2, which is 6. So we need 3 of those, so then the next number will be n plus 4. You see there's a pattern here, and this works the same way for odd. If the first number was odd, like 3, then the next odd number will be 2 places over on the number line, which would be 5, and the next one will be 4 places over on the number line, which would be 7. So once we have this written out and have a way to express 3 consecutive even integers, then we can go in and read to write our equation. So it says the sum of these 3 consecutive integers is, is equal to, and sum means that we are adding. So I'm going to erase these commas and show that we are adding the first, second, and third even integer is 12 more than twice the smallest integer. The smallest integer will be n. Twice more than that will be 2n. And it says 12 more, so just 12 more than that. Once we have our equation written out, we can solve it using our scan method, simplify using distributive property. In this case, we don't have any. That's S. C stands for combine like terms. We do have these n's, which we can combine. It's 3 n's. So it combines to form 3n. 2 and 4 combine to 6. And now that we have it simplified, we can isolate the variable using inverse operations. It's easier to minus 2 n's on both sides right here. So now we're left with n plus 6 is equal to 12. Again, we just need to get n by itself. So again, we use inverse operations to get rid of that plus 6. With the minus 6, as long as we do the same thing to both sides, the equation stays equal. And we achieve our objective of isolating the variable using inverse operations. We find that n equals 6. We're almost done. We have to read the question carefully, where it says, write and solve an equation to find all 3 integers. So if n was equal to 6, then the next consecutive number is n plus 2. 6 plus 2 is 8. Then n plus 4. 6 plus 4 is 10. So our consecutive integers are 6, 8, and 10. Now we fully answered the question. We found 3 consecutive even integers. And that is the end. And that's everything that will be on the Unit 1 quiz. Made simple. These skills we've practiced enough. Broken down the vocabulary, translated it to make sure students know what the questions are asking. And I'm hoping to see a lot of 100s, a lot of A's, and a lot of satisfaction for all the hard work that we put in.